This week, we'll be able to explain the concept of correlation. We will also discuss the difference between positive and negative relationships. Also, we'll interpret both the significance and meaningfulness of an R value. We will also be going over and differentiating between correlation and regression, and lastly, describe multiple correlation techniques. Throughout our daily living, we will notice different relationships between different variables. Some relationships are easy to detect, such as if I don't brush my teeth, I'll have bad breath and develop cavities, while others may be weaker or more subtle or not directly observable. The relationships that exist between and among different parameters has helped practitioners and scientists gain a better understanding on the factors that impact human health. We can also detect some sort of relationship, however, we need an objective way to quantitatively assess the strength and meaningfulness to a relationship. The study of relationships is termed correlation analysis. Once we determine a relationship, we can then use the information and can predict future outcomes based on the initial values of the variables. This is referred to as regression analysis. Correlation is a statistical method which measures the relationship among two or more variables. Really though, correlation is finding out how two or more entities relate to each other. In research, entities are called variables, where a variable is a means of measure factor that are subject to change. The variables in your research study will depend on the question you're trying to answer. So some examples of variables are strength, body composition, and then vertical jump height. If the entities or variables are correlated, they change together in a predictable fashion. Remember, correlation does not mean causation. Even though there is a correlation between two variables, we cannot say that one causes the other. For example, there is a correlation with smoking and lung cancer, such as both increase together. Even though some people will say that smoking causes lung cancer, we cannot make that statement based on correlational analysis. A preferred way to say it is, increased smoking is associated with increased chance of developing lung cancer. Correlational analysis in its most basic form involves quantifying the relationship between two variables. Researchers will look and examine all sorts of relationships between different variables. For example, you can look at the relationship between intensity of training and VO2 max, which is the maximum amount of oxygen an individual can consume. To determine the value of that relationship, we use a statistical measure which is called the coefficient of correlation, which is a number between -1 and +1, with 0 indicating no relationship, and a plus or minus or kind of -1 or +1 indicating a perfect correlation. If the sign is positive or negative, this indicates the direction of the relationship. The scatter in a positive correlation will visually look like it is going from the bottom left to the top right, as this one does on the right side. If the first variable has a small value, then the second variable will have a small value as well. So what happens is that each participant has one pair of values, of variable 1 and variable 2. And these are plotted along an XY or scatter plot graph. For this example, we are looking at the relationship between cardiovascular fitness using VO2 max as a measure, and then the distance traveled in a 6-minute run. After testing individuals of different fitness levels on VO2 max and their distance traveled in 6 minutes, you will then put their data into SPSS and create a graph. The graph will then display points and show the relationship. Based on this example in the graph on the right, individuals who have a higher level of fitness can run farther than those with lower levels of fitness. In the figure to the right, this displays a negative correlation. A negative correlation is a correlation where as one variable increases, the other variable decreases. Negative correlation indicates that small values of one variable are associated with large values of the other variable. This will visually look like it's going from the top left to the bottom right. When you look at a graph, as values of x increase, values of y tend to decrease. Based on the graph to the right, individuals who have a higher time or take longer to complete a 1-mile run have a lower level of fitness. The correlation values that run from -1 to +1 provides an indication of the strength of the relationship. The closer the number is to 1 or -1, the stronger the association. Remember, 0 indicates no relationship, and a 1 or -1 indicates a perfect relationship. So let's take a look at grip strength and the correlation between left and right hand grip strength. You can see in the table the grip force for the left hand and the right hand, as well as GPA and body mass. Now that we have the data, we can then calculate the correlation coefficient. Here to the left, we can see there is a positive relationship between left and right grip strength of R equals 0.97. The strength of the relationship is indicated by the proximity of R from -1 to 1. Since R equals 0.97, this is very close to 1. So the association between the right and left grip strength is very strong. In general, we really don't expect to see relationships that are -1 or 1 because some variability exists in almost all human characteristics. The figure to the right displays the correlation between right grip force and GPA, which results in an R value of 0.125. As you can see, this is still a positive correlation. However, it is a very weak relationship. This should be no surprise since intelligence levels do not dictate strength levels. It is important to know that a positive or negative sign has nothing to do with the relationship strength, but it just indicates if the variables increase in the same direction or opposite direction. So for example, an R value of -0.87 indicates a stronger relationship than an R value of 0.75, just because 0.87 is farther away from 0 than 0.75 is. The letter that we use to indicate correlation values is the letter R. This comes from a statistical test used to calculate correlation values, which is called the Pearson's Product Moment Correlation Coefficient, or Pearson's R. Pearson's R is the parametric statistical test for strength of relationship between two variables. In addition, this allows us to visually see the relationship between the variables in the XY plots. We can hand calculate Pearson's R by inserting the values into the equation that you see on the right-hand side. However, a quicker way to calculate Pearson's R is to use a statistical program such as SPSS or a spreadsheet such as Microsoft Excel. For correlation, the term significant means that the R value is significantly different than 0. Since it is significant, we will think that there is a relationship. However, the question to ask is there actually a real relationship between the variables? Just because the R value equals 0.70, which seems far away from 0, it does not mean that you can conclude significance. You must compare the R value obtained, which is called the R actual, with a critical cutoff value of R, which is called R critical. The R actual is the Pearson R, which you calculated from the dataset. If your R actual value is greater than the R critical value, then you can reject the null hypothesis that R equals 0.0, and you can say the relationship is significant. If your R actual value is less than the critical value, then the correlation is not significant. You can also use the p-value to determine significance. Remember that generally the alpha level is set at 0.05, but you can also set it at 0.01 or 0.001. One thing with R critical is that it is not a constant number and it changes based on the number of participants in a study and the alpha level chosen before the study. So calculating R critical is unnecessary since computer software will provide the critical R value for you. When using the p-value, if your p-value is less than the alpha level, then the results are significant. So now that we determine the R value is significant, we really want to know how strong that relationship is between the variables because the R value just tells us that an association exists. We want to also examine the strength of the association. So we can have an R equals 0.40 and an R equals 0.95 and both be significant where the p-value is less than 0.05, but one is stronger than the other. We can determine the strength of a significant relationship through calculation. This calculation is called the coefficient of determination, and the symbol for the coefficient of determination is R squared. Calculating the coefficient of determination is by squaring the R value. So if you have an R equals 0.70, then R squared equals 0.49. The coefficient of determination measures the amount of shared or common variance by the two variables. You can report it as a percentage of shared variance by multiplying R squared by 100. The notion of shared or common variance is an indication of how much of the change in one variable can be explained by a change in the other. In general, the larger the R squared value is, the more variance the variables have in common and indicates a stronger relationship. So let's go back to the hand grip example where we saw an R value of 0.97, which is a very strong relationship. R squared will equal to 0.94 then. This means the shared or common variance is 94%, or in other words, right and left grip strength vary together 94% of the time. So what does the remaining 6% mean? This is called unexplained or error variance. The term unexplained means that it is the variance unaccounted for by the two variables. Oftentimes, you will see in research papers the authors trying to explain the unexplained or error variance by looking for other variables that account for the difference in one variable or the other. Here's a table that you can utilize to interpret the results from research papers if there is no indication of the significance of R or the authors don't interpret their R squared values. The purpose of this table is to give you a quick look at what these values mean in general. So if you see an R value of 0.5, you would think the relationship to be moderate. And if the authors of that paper make an outrageous claim of the relationship based off that R value, then you might question the interpretation of the results. Majority of the time, researchers will measure several variables and perform more than one correlation within their research study. A correlation matrix table is created, which is an efficient manner of reporting Pearson's R when 3 or more variables are being compared. This matrix organizes the correlation in an orderly way so you can read and interpret the information easily. Each number within the matrix is a distinct R value. So let's take a look at the table here, where each column and row intersect. There is a value for that specific correlation. So if you read across row 1, left grip strength, to column 2, right grip strength, you'll see the R value of 0.97. The next value in that row is R equals 0.71, which is the correlation between left grip strength and mass. Generally, you will see the significant values labeled with an asterisk or a star, with a p-value listed below the matrix. Notice that no values are provided when a variable is plotted against itself. This will always be displaying the number 1. Further, only one set of values are given and only half of the matrix is filled. Note that a star next to a value indicates that it is significant. When there is a significant, strong correlation, it can help predict the value of one variable from the corresponding value of the other variable. The statistical tool used for this is called linear regression. Regression is a statistical method for predicting one variable based on the value of another based on correlation. An example of regression is calculating body fat percentage from skinfold testing. The values from the skinfolds are placed into a regression equation to predict an individual's body fat percentage. The most basic form of regression is simple linear regression, where one variable is predicted from another variable to which it is correlated. So the greater the strength of association, the better the prediction. So we've all seen this equation before, but the equation used for simple linear regression is y equals a plus b times x, where y is the value of the variable to be predicted, a is the y-intercept, b is the slope of the regression line, which is the rate of change of y for each unit of change of x, and x is the value of variable that has already been measured. So what is a regression line exactly? This line represents the line of best fit for all the xy coordinates on the graph, which is where the x and y means intersect. The closer the correlation is to -1 or +1, the tighter the fit of the line is to the points on the scatter plot. So the regression line is generated from the means of the x and y values, and it is this line from which the regression equation comes. It is always important to remember that the regression equation is only as good as the correlation from which it comes. If a weak correlation exists between two variables, then predicting one based on the other will not yield meaningful results. Unless a perfect relationship exists, then the actual y values differ from the estimated y values, and the differences between estimated and actual y values are called residuals. Residuals represent the error in the projection equation. A way to determine the accuracy of a regression line is to calculate the standard error of estimate, which provides a measure of the amount of error in a regression equation and is the standard deviation of the residual scores. The smaller the standard error of estimate is, the more accurate the regression equation is at predicting y values. Although some estimated variables may be predicted well through the use of one predictor variable, more often the prediction can improve through the use of two or more predictor variables. For example, a researcher may be interested in predicting how far an outfielder can throw a baseball and has previously determined that a positive correlation of 0.60 exists between distance thrown and strength, with an R-square of 0.36. This means that 67% of the change in throwing distance is not accounted for by the change in strength. If the researcher used strength as the only predictor, the resultant equation would have a large error variance. However, if the researcher added other predictors such as arm velocity, pelvic rotation, and step length, the resulting equation could more accurately predict throwing distance. The type of equation that you might see for a multiple regression equation will look similar to that of a simple regression, except more predictor variables would be included. You see that y is the dependent variable to be predicted, x1 through x3 are the predictor variables, and a and b are constants. More bx components can be added for each additional predictor variable. It may be tempting to add many different predictors in order to get the best possible fit. However, there are often only several primary predictors, after which variables add little to the equation. With this equation, resultant correlation coefficient of all the variables, r, can be calculated. Some things that need to be completed by Monday, November 16th by 11:59 p.m. is completing quiz 10 and also submitting the correlational assignment in Canvas. Please submit as a Word document file or PDF file. And again, no pictures or screenshots. Lastly, please make sure to be working on your literature review. This is due Friday, November 20th by 11:59 p.m. Again, this is due Friday, November 20th by 11:59 p.m. and this is not due on a Monday. Again, as I repeat this for the third time, this is due Friday, November 20th by 11:59 p.m.